Hello, I'm Dalton Aker, and I'll be pitching MindField for the Purdue Moonshot pitch competition. So first, a brief introduction to brain-computer interfacing. So brain-computer interfacing is anytime you have a brain and you have a computer and they exchange information, that is a brain-computer interface, or BCI. This is really exciting stuff because this means that by reading neural data, we're able to restore a patient's ability to interact with the world. And this is not just limited to these two domains. In fact, there are roughly 8 million people in the US who have conditions for which BCIs have shown promising treatment options. There are two main ways that we can detect this neural data. The first is by detecting each individual neuron spikes, and the second is by summing these spikes in a given area and detecting what is called the local field potential. Now, BCIs in use today prefer the spike-based approach for higher resolution, but it comes with all sorts of drawbacks. And this means that there are less than 100 BCI implants in use globally, despite that 8 million number in just the US that could use them. Now, neither one of these approaches is exactly optimal, as we still want all of the resolution of spiking data with all of the power requirements and accessibility of LFP data. So here at MindField, we developed a new paradigm by which we take this LFP recording, and thanks to recent advances in AI, we're able to feed it through a neural network, which reconstructs the spiking activity, allowing us all of the resolution of spiking data with none of the drawbacks. So this allows us to create a novel paradigm by which we take the LFP data, send it to an external computer for decoding and analysis, and give patients all of the control of a spike-based decoding BCI at a fraction of the cost.
Thank you for the opportunity to present MindField.